This conference will now be recorded.
All right, so welcome everyone to another OCP TAP session. This is call number 81. Today we have Charlie Meyer from Satelles, which is going to give us a talk about time synchronization via LEO satellites. And as always, we start with a format where we present our speaker. So Charlie Meyer is a Senior Technical Director at Satella, where he develops LEO satellite timing solutions for critical infrastructure users. Previously, he was a distinguished member of the technical staff at Alcatel, Lucent, Nokia, Bell Labs, where he worked for 25 years. He was a principal architect and subject matter expert for wireless 3G, 4G, 5G, RAN timing, and synchronization systems. He has designed numerous GPS, GNSS, PTP, and OCXO solutions, has worked with multiple US government agencies regarding the dependence of telecommunication on GPS. He's a member of ATIS Sync, IEEE 1952, OCP TAP, and a senior member of IEEE and holds 4 US patents. So I think with no further ado, Charlie, the floor is yours.
Okay, hello everyone. So this is a funny group because OCP TAP, you guys are already extremely knowledgeable about timing synchronization, especially in the realm of data centers and virtual RAN and anything else that where you could put a time card. So what I'm going to be talking about is getting the time sync from LEO satellites. For the most part right now, you're probably getting it from GPS, GNSS, and so this may be a little new. So I'm going to explain about the LEO version of getting time sync. All right, so page down, enter. There we go. So data centers actually falls into a category called critical infrastructure, which fundamentally means this isn't a consumer stuff. This is serious stuff that if it doesn't work right, it affects very large populations of people, and is often watched by the government to make sure that this kind of stuff doesn't go badly, but it continues to work. Other critical infrastructure, as some of you may know, the communications, 5G, which is where I came out of. There are emergency services to locate people. The finance services when you do transactions to timestamp things. All kinds of information technology, energy, lots and lots of other things. You can see there are 16 sectors here that are identified as part of national critical infrastructure. Now, when we talk about data centers requiring critical infrastructure, it has some unique issues associated with it. As Ahmad has often presented, when you synchronize the data, you can get significantly higher data rates that you can process and transfer through servers. In the finance world, they have requirements like MiFID that require microsecond and even sub-microsecond time stamping as new MiFID requirements are coming out. Some data centers involve synchronized remote operations or aligning of processes and control of different functions, maybe in a factory type environment. There's a lot of financial transaction and other all kinds of transactions that often fall into what's called the zero trust initiative. That's another layer of security that's there. And then the newer 5G going into 6G gets into virtual RANs. So accurate timing and synchronization has a lot of a lot of very important places within the data centers, whether they're no matter what they're used for, all kinds of data centers. So GNSS is actually the most accurate way to get a UTC timing alignment, and everybody kind of knows that. But there are a couple problems with GPS or GNSS. It doesn't work well in an urban canyon because you have a limited sky view. It really needs a good large sky view. So the urban canyons and the multipath environment can devastate the signal and make it unusable. It also doesn't work well indoors at all. And it doesn't work where jamming and spoofing exist. And this is sort of a newer challenge that has arisen lately, especially depending on where you're talking about. That may be more of a problem than other places. Now, one of the other timing sources that you see a lot with data centers is getting timing via NTP, or in some cases PTP services. But these are really only timing distribution services. They take time from one place and they transfer it to another. Now, these kind of remote services, they may not always be UTC traceable, or they may be degraded down to stratum 2, stratum 3, hopefully not stratum 4 if it's being used at a data center. They're not always available because you're getting them from a remote location. They may not be secure if they're coming over public internet. Sometimes it's just not feasible depending upon the type of service you're trying to provide in the data center. It's just not feasible to go outside of the facility to get timing from a remote service. You don't even want to do that. So it's not even desirable. Or it could be very expensive. Fees involved with especially the more accurate NTP and PTP services. So that brings us like, okay, so where else can we get UTC time sync from? So now we're going to talk about how you can get it from LEO satellites, and specifically the Satelles STL service. All right, so this is we're really the only LEO source of PNT at this time. So I'm going to talk about our service. All right, so we provide a service called STL that's an alternative to GPS and GNSS for network timing and synchronization. And it's resilient to the loss of GPS, GNSS. It works indoors. It works in a lot of places where GPS and GNSS does not work at all. And it provides a secure backup for critical infrastructure. So what we do is we have an exclusive license to use part of the Iridium LEO constellation, and we use it to transmit a UTC traceable PNT signal that we call STL, which stands for satellite time and location. Now, you can see on the bottom there's a little kind of a sketch, way out here at 12,550 miles. That's GPS and GNSS. These are on what's called the Middle Earth orbit, MEO. All right, and Iridium is down here on the low Earth orbit, only 485 miles above the Earth. So it's significantly closer to the Earth. This allows it to have a higher power to reach the receivers, typically 1,000 times stronger, which is 30 dB. This is a significant increase over GPS that will allow it to penetrate through walls and windows to indoor receivers. It's also a robust signal. So GPS is actually an overlay of constellations. There's the GPS, the Galileo, there's the S-band rule, transmitting on the same frequency, and it's their code division divided on the same frequency, but it's a lot of energy all in the same band. And so the receivers have to decorrelate them in order to find the signals and utilize them. We don't have that problem. We're not sharing our signal with anyone, so we don't have any uncorrelated signals. And also, because of the way LEO works, and I'll talk about it a little more, they're moving so rapidly around the Earth that if a multipath exists, it only exists for less than a minute. When you get a GPS multipath, it could be there for a few hours, and that can pretty much just make it unusable in itself right there. You just would completely lose the signal for a few hours, right? So we're significantly higher in power, and it's much more robust. Ahmed, I guess I'm going to save questions for the end. Is that the way you want to go with that?
Yeah, like we can answer questions. Let's say, I mean, up to you. Do you want to answer them on the fly, or they can be placed in the chat, or we can have just at the end?
Let's put them at the end because some questions may get answered by a later slide.
Yeah, sure.
Okay.
So the question again, if for those who might leave earlier or something, feel free to put them in the chat. So then, if you leave, I can ask them, and then you will have it on the recording as well.
Okay.
Back to you.
So if you were to look at the constellations around the Earth, so here's again GPS in the middle of Earth orbit, the Galileo in the middle Earth orbit, and much closer to the Earth is the Iridium Leo constellation. And again, this is the low Earth orbit model there. And there's some other parameters there. One of the ones that's worth noting is it takes about 14 hours for a GPS. Galileo is 14, GPS is 12 hours to circle the Earth. Okay, it only takes 100 minutes for a LEO satellite to circle the Earth. They're moving that much faster, and so they circle the Earth 14 times a day, as opposed to GPS and Galileo, which are about twice a day. So the orbital velocity is a significantly different aspect of the way the satellites operate. All right, so again, you can see now this is geostationary. This is MEO, which is GPS and Galileo, and then LEO, and it is not exactly the scale. All right, so just trying to give an idea of the perspective and the kind of footprint that it will have on the Earth. So the LEO is going to have a very small footprint as it moves rapidly around the Earth. The MEO will have a much larger footprint as it moves slowly around the Earth. GEOs are fixed. Their footprint never changes. It's going to cover a large swath of the Earth, but it never moves. So the LEO from the Iridium that we use is further divided into 48 regionally targeted overlapping spot beams. All right, so these spot beams allow the signal to be aimed and pointed to where they're specifically needed, rather than just broadcasting them anywhere. So they are focused beams that are going to focus the signal to the locations where they're going to be needed. Now, the lower altitude and the faster velocity of LEO, all right, so again, it's a period of only 100 minutes. This allows for many new position calculations. And so this is called Doppler assisted ranging. So the way all the satellite constellations work, GPS and Galileo and the others, you have to range the receiver to the satellite, and it'll use that to triangulate its position. With LEO, we're going to do it a little differently. We're going to use Doppler assisted ranging, and it's going to be more of a trilateration of the signal. Now the LEO are moving so fast that within a minute, it's going to be about 2 degrees further along. Well, in 10 minutes, when one satellite comes along, and then another one will come along 10 minutes later, it's going to already have shifted 2 degrees east to west in the sky, going actually eastward. And every minute or so, it's going further along in its trajectory. And so every minute, it's almost like there was another satellite there. So within 10 minutes, it's almost like you had a 10 satellite lock, And so this all gets filtered together in a Kalman filter to converge the position and the time states to their actual and true values. All right, so you don't actually have, like in GPS, you're gonna have 12, 20 satellites. You're not gonna have that with this. It's typically 2 to 4 Iridium satellites will be in view, which is all that's needed to maintain an accurate clock. So the footprint, and here I'm comparing the LEO to the GPS MEO. All right, they're regionally controlled spot beams as opposed to a full facing surface, and they don't control coverage. The spot beams actually make it very difficult to disrupt the signal. You can't predict how the beams are moving. That's all part of the algorithm of how it works. The power is about 30 dB hotter. They're both L-band, however, because of the higher power, the LEO can penetrate indoors, whereas GPS, it's just not strong enough to penetrate indoors. Our STL signal it's at least 40 years newer technology. So of course we have authentication layers. So that's got all kinds of advantages to be able to provide authenticated time, authenticated location. The constellations are 66 second generation Iridium Next, they're called. This entire constellation was relaunched in 2019, the second generation one. So they're all very, very new satellites that are up there right now. GPS has to continually, of course, launch new. There's a lot of old ones up there. Both are worldwide coverage. The signals are available worldwide. We also can track our signal not just to the U.S. Naval Observatory, but also to the National Institute of Standards, NIST, so that there's probably going to be some more traceability coming in out of Europe in the future. So the Iridium satellites are actually full-size satellites. These are full commercial-size satellites that coming in at 689 kilograms. These are not the little toy cubes as you often hear about that, like the solar flare can kind of knock them out of orbit a little easy. Not so with these. The Iridium constellation has already withstood 2 solar maximums without any incidents from that. The frequencies that we utilize are available, licensed, and protected worldwide. So we don't have any spectral limitations in transmitting PNT anywhere in the world. And because they're L-band, they're resilient to storm clouds, rain fade, and they're able to penetrate into structures. The Iridium satellites have large hydrazine fuel cells that are used to maintain onboard boosters, which make fine corrections in the trajectory and can withstand the orbital drag caused by a solar storm. So if a really bad solar storm came along and kind of kicked it a little bit, it's not a big deal. It just nudges it right back into the proper trajectory. So again, it's an innovative mesh of 66 cross-link LEO satellites. So cross-link is a technology where it allows a satellite to talk to all the other satellites. They can cross talk to each other. So if we needed to reach a satellite that was not over a control station, we can just uplink to whatever was passing by and have the message relayed over to the one that needed an update or fine tuning. So the cross-linking is a significant advantage in managing the constellation. We use modern cryptographic techniques to deliver a spoof-resilient, trusted time and location. Again, traceable to both USNO and NIST via multiple geographic distributed ground tracking stations. Now, typically the accuracy we're getting on the ground we can get is better than 100 nanosecond 1 sigma. depending upon the oscillator that is used with it. They're able to meet the ITU-G 8272 PRTC-A timing performance as well. So this is a little bit about the crosslinks, providing orbital and time information to the entire constellation, even if they're not in view, and secure independent signals on each spot beam, ensure high integrity and resilience. So you can't actually predict the beams. Now this shows all the beams on out of one satellite here, all 48. Now, let's say we didn't need to transmit over the ocean. The ones on the eastern side here might be turned off, for example. So the beams are moving in a pattern that cannot be predicted in advance, and so it's not something that a spoofer could predict. The higher power is also of interest when you consider the resilience to disruption, right? So if say you had a 1 watt for this larger power, let's say you had a 100-watt transmitter that was affecting a very large area here and knocking out GPS and GNSS in that area. Because we're 30 dB stronger, it would only have an effect of the smaller blue circle in the middle. And you know, whether it's coming from one source or another, we live in a world right now where these kind of disruptions happen. Somebody could get a little cigarette lighter jammer and drive past your data center and knock GPS out. And if they park there to have coffee and a sandwich, you could lose GPS for quite a long time. And a lot of you may have heard about the incident at Newark Airport where this trucker had one of these in his truck and he drove past Newark Airport every day, and every day the airport at a particular time just completely lost GPS to some very critical tracking systems at the airport. This got quite a significant amount of attention, and they finally tracked this guy down. But you know, these things are proliferating a little too much by anybody who doesn't want to be tracked. So I'm going to talk now about a couple of deployment examples. So we're extremely well deployed in a lot of different applications at this point. One of the typical things we do see a lot of interest in is to synchronize equipment indoors. Right. So if you had a large building where you needed synchronization and your equipment was, say, located here, it could be really expensive to core up through a large number of floors to get an antenna on the roof. And this might not even be allowed by the landlord. So this is a significant challenge that's been going on for a couple of decades now. And I've seen perverse amounts of money being spent to get an antenna on the roof. So another method would be to use PTP distribution from a distinct grandmaster that would go through router hops, and then you finally get it here to your location where you need it. Somebody's got a little noise there, if they could mute. So the problem is hopefully you can control the hops. If you can't control the hops, you're going to get a very inaccurate signal finally getting to your location. If you can control the hops, that's good. Hopefully you own the whole backhaul and you can maintain that. Somewhere out there you have a GPS synchronized device, and as long as GPS is available, this method can work. But it does have its limitations, and we often run into quite a number of locations where remote grandmasters are just not an option that can be utilized. So the STL signal can be picked up by an indoor antenna and used to lock up the STL receiver and distributed locally, either through some local router, grandmaster, edgemaster type method, to 4G, 5G RAN or racks of time cards. So the antenna for the Iridium band is much smaller. This is a helical design. It doesn't require a ground plane, and so it can be mounted in very interesting ways. Like here's one mounted in the top of a rack of this is in a data center actually. It's just mounted there at the top of the rack, and it's receiving the signal indoors and working fine. So there's another view of the same one. So there's the same antenna. This is serving a receiver. This is the STL receiver here, and feeding a time card. There's one time card that services the entire rack. All right, so that's one. Here's another example where it is a very large building, and coring up to the roof was just out of the question. And so the indoor antenna here it's actually mounted in a drop ceiling, and it's used to, in this case, synchronize a pair of 5G micro RANs. RAN is the radio access network that your cell phones are talking to. So these guys all needed their own cell service up on the 40th floor, and cell service is always aimed at the street. So when you're up on the 40th floor, you might get no bars or one bar, you might get nothing. And so that was unacceptable. They needed service up there, and so they had their own 5G network installed there and using the indoor antenna. This is a smart hospital installation where some Ericsson 5G RANs are being used in the same way, using an indoor antenna and synchronizing the Nokia IXRE router. It's a smart router, and it's distributing 5G service all over the hospital for all kinds of crazy stuff going on in there. So STL as a service has been validated by a number of independent authorities. One of them was the Department of Transportation. Back in January 2021, they published a report summarizing 11 different alternative PNTs, alternative meaning non-GPS type technologies. So the STL LEO PNT had a readiness level of 9, which is as high as you can get. In other words, it's ready now. You don't have to wait for it. The spectrum is protected, so you don't have to worry about, well, we'll wait till you can get licensed spectrum. It's already there. Service deployment is low. Okay, nothing needs to be built out. The coverage is worldwide. It's synchronized to universal time. The signal robustness is strong, say available indoors, and is authenticated. It has a failover where it tells you that you're locked or you're not locked. You have a loss of service. The distribution is via satellites, the Iridium satellite constellation. The interoperability with GPS is significant. It's highly compatible with GPS, including leap seconds and all the details. It's highly compatible. PNT information security is high because the signal uses authentication. Time to service implementation is short. It's available right now. You don't have to wait again. And the longevity is medium based on satellite life of 15 to 30 years. Right. So that was the DOT report. It was also evaluated by NIST in November of 2021. They published a technical note 2189 that evaluated all kinds of critical infrastructure that depended upon GPS, and they concluded in there that STL is a reliable source of timing that is highly consistent with UTC. That it can be used as an indirect distribution for UTC. It's a commercial alternative that's available today. It's easily within 500 nanoseconds to meet any critical infrastructure requirements, with accuracies that were actually better than 200 nanoseconds, and with long-term stability of better than 25 nanoseconds with standard deviations of 50. So we also have a ground monitoring station directly connected to the NIST main clock ensemble. We're not using a fiber from NIST. We're actually inside NIST, inside and directly connected to the ensemble. So there were also some time experts at Satelles and NIST that co-wrote a paper that was published back in January at the Institute of Navigation. This paper is available for anyone who's a member of ION, or I guess if you send me an email, I could get you a copy of it. But this paper demonstrates that the calibrated STL signal can achieve time offset better than 18 nanosecond to UTC. With a peak to peak, they used an OCXO example there of 325. Again, it's oscillator dependent. If you have a rubidium, it was better than 80. And there was a chart that shows some of this data. And again, this is all in the report. It was also, the signal was evaluated by the European Commission, and they looked at timing accuracy, stability, availability, also position accuracy, horizontal and vertical, and lock from first power up. This was done using an older receiver, but nevertheless, the report's out there, and you could see that as well. So we've had a number of recognitions. From Fierce Wireless had one recently in December, and also we were recognized by Small Cell Forums recently as well. So performance examples. So this using a rubidium miniature atomic clock. This is the microchip SA55 in particular, was being used on this test, and showing outdoor and indoor accuracy examples. So this is burst per minute. So our signal is coming in burst. So this is showing for the indoor significantly lower burst count, which you would expect in an indoor location, and a lower carrier to noise level as well. So in this particular example, putting up the PRTC A and B mask for TDEV, they were both able to be met. The B was even able to be met with the outdoor antenna as well. And the MTI, similar example as well. There's the ADEV for the same test run. So what we're seeing, what we've been able to demonstrate is that we're in this certified Stratum 0 UTC source of timing that can be used to create a Stratum 1 clock compliant with the ITU PRTCA performance standard. The timing accuracies available are anywhere from 10 to 50 typically, depending on your oscillator type and traceable. So here's an example where, like if it was a rubidium compared to, say, a TCXO, you can see that there's a bit of difference in the accuracy and the maximum error, both for indoor and outdoor antennas. So these are just some examples of the performance that can be expected. And just to summarize, so STL, LEO, PNT it's a powerful signal, secure, globally available. It's resilient to the loss of or disruption of GPS. It's traceable. It's available now, and the accuracies are well within the kind of numbers that are needed for the data centers, and stability comparable to GPS. And the Stratum source, again, Stratum 1, you can get Stratum 1 signal out of it, very easy to distribute within the data center. And that's it. So let me turn it over to questions now.
Wonderful. So Philip has a question. Philip, you want to go ahead?
Hey there, great presentation. This is super cool. There's a few things I wanted to ask about what's providing the time. And I have a bunch of questions here, so I'll ask like one, maybe a follow-up, and then cede my time and then come back. What wasn't clear to me is whether your satellite, your STL on the Iridium platform is using Iridium's system clock for holdover. And if STL is using GPS and GNSS to sync itself to UTC.
So we could use, at the moment, we could use either GPS or NIST to validate the accuracy of our signals for corrections. And in the future, we're looking at some of the European standards labs as well.
Are those enforced from the, are those corrections given by, like how are those corrections made? Are they coming to the receivers, or are they are the satellites receiving their own GPS signals and making corrections on board?
We transmit corrections to the satellites to keep them accurate, or to transmit their error, and they'll transmit that down to the receivers so the receivers can compensate. So it's very much like GPS, where you're doing the ranging calculations. All right, so we don't need the holdover capability of the satellites, although that's going to maintain the accuracy as they traject through the orbit. But we're going to be monitoring the error and providing corrections for each satellite that they're going to transmit down to the Earth. So again, it's very much like GPS in that regard.
I had a similar question, if I could ask it. I mean, interrupt.
Yeah, go ahead. Go ahead.
Hey, so yeah, so great presentation, Charlie. The question I had kind of relates, I think, to the prior question. Right, in GPS, you've got a control segment, a space segment, and a user segment. You can look at it. You probably look at it similarly, right?
Yes.
So in the case of the space segment for GPS, or for that matter for the other constellations, there's very high performance clocks on the satellites, right? On the satellites, right? So
Right.
sure, there's corrections that are coming from the control segment to the satellite, but those satellites have very good clocks on them. In fact, multiple. And ultimately, when you're a receiver in the user segment, the real clock signal you're getting is coming from the clocks that are on the satellite. So my question is how does, if you were to compare that to STL, what are the clocks on the satellites? Or maybe they're not. Maybe because of the way the technology is needed, they don't need that accurate of clocks. But I'll stop there. Maybe you get the question.
Okay, so they do have clocks that are good enough to do this application, whether they're at the grade of a GPS military satellite. I think there's a lot of discussion that could happen about that. And I'm not sure we know everything about what's really on board some of the GPS. But okay, so it's what we see from actually doing the measurements and providing the corrections is that we can maintain an accurate clock to the levels that I gave examples for. All right, so that, I guess, summarizes a lot of activity. All right, you could probably point to about 12 different sources of error that need to be managed. You got the clock drift of the satellites. You have orbital velocity corrections. You have ground station monitoring of what's actually coming down, the corrections that need to be applied, ionospheric issues. There's a lot there. All right, so I don't think I'd like to say you had a simple question. You're going after a couple of the pieces there, but there are a lot of pieces in there. And the overall performance that we're able to measure, I think demonstrates that they're all being managed very well, and the performance that's coming down is very good. Is it as good as GPS? No, I think GPS is a little bit better. It is. When you have it, when you can get it, when you can use it. All right, we're not trying to replace GPS. All right, so it's an alternative timing system that can be used if you can't get GPS, or you need, for example, indoors or any place else. And depending upon your application, we've been seeing that it is accurate enough for just about all critical infrastructure. I hope that answered it.
Thank you.
Okay.
Philip, go ahead.
Yeah, I have some follow-ups. I want to talk about the spacecraft a little bit more.
Sure.
So it's clear that the Iridium spacecraft is very capable. I was wondering if the STL component, like this timing transmitter and stuff that you're using on the Iridium platform, if that's feasible to, like, as a component, use on a different satellite bus or different satellite platform. And if it's depends on performance, can you share some of those performance requirements for the satellite bus to serve the transmitter?
So that gets a little bit into proprietary stuff. Let's see what I can say. We have exclusive use of one of the Iridium channels for PNT. Can we add it to other satellite constellations? I think that's possible. It depends upon the other satellites, what bands they can transmit on. Some of them have limited software-defined radios. Their SDRs have limitations, whether it's by filtering or I don't know, whatever they are. So, but if their SDRs can accommodate our modulation and frequency schemes, we can add our signal to other satellites. Yes.
Can you share performance requirements for the system clock? You mentioned that a lot of the Iridium satellites have good enough clocks on board, and you're utilizing that to get the accuracy. I presume that means that the satellite bus has like a minimum required system clock accuracy. So, can you share that?
I mean, so some of the new CubeSats that are going up that have like TCXOs in them, they're going to have a lot of variation that would significantly add to the amount of data that needs to be corrected continually. It would be nice if you could make a correction and then it can continue for 2 hours around the Earth without having an update. But yes, that would require at least an OCXO, if not a rubidium type grade oscillator. Suffice, I'll just leave it with that. I think you know exactly what I'm saying there.
So one question.
If you want to discuss that more off
yeah, sure.
we could talk about that.
One question for you. If penetration in the building is not an issue, and I have roof access, is there also, let's say, a possibility to have the STL module, let's say, on a geo? And then, I mean, just like hypothetically, like, is the distance important? If I go like 20,000 miles like distance, would that be still a viable solution?
The problem with geos is you're so far away that you're going to have a power issue. You're going to have to really put a lot more power into it to have it reach. Now, enough power to also penetrate indoors puts an additional constraint.
Yeah.
For the most part,
I let go the indoors. I said like I have access to.
Okay, outdoor. All right. So you have a lot of advantages outdoors.
Yes.
Sure. If we put our signal onto a geo satellite, that definitely could be detected outdoors, despite the additional path loss that you're going to incur. It should still be usable as well. Yeah, as an additional augmentation and consideration in the future.
Yes, it's more like safety. Bijan, go ahead.
Correct. Yeah.
Yeah, so my question is that, given this is a LEO satellite provided signal, the relative motion, the orbital velocity is kind of high, as you mentioned, right? So
Yeah.
what kind of compensation do you have for Doppler shift?
Well, as you can imagine, it's quite a lot of Doppler. So we have the bursts are coming in where they're continuously having to manage the Doppler offsets to the ranging along with the ranging data, and we use a very special Kalman filter algorithm that was created specifically for that. All right, so it's very different than a Kalman you would use in a GPS where they're moving relatively slow by comparison.
Mm-hmm.
So it is a custom proprietary algorithm that we use to do that.
All right.
And those are built into the receiver chipsets, I guess.
Correct.
This is
Yes.
Okay.
Yes, the receivers do have that all built in.
All right. Thank you.
Excuse me, I do have a question. So is Leo's timing still get it from the timing source at Geo, or it's how?
You mean at GPS?
Um,
So the only Geo right now are augmentation systems that are utilized by different countries. Right now, all the GPS and GNSS type signals that are out there right now, they're all middle Earth orbit, MEO. We do not get our signal from GPS. No.
No.
All right. So yeah, no, we do not do that.
so where is the UTC store? I mean,
Well,
if
okay,
you're
so
synced to the UTC, right? So where is UTC? Which satellite has it?
so the GPS satellites are locked to they use UTC from the U.S. Naval Observatory, USNO. Now we do that too. USNO is one of the there are two sources in the United States, USNO and NIST, and we are being monitored by both. All right, now in Europe, we're working with ISPRA. We're looking to have other partners out of the different physics laboratories and standard laboratories in Europe. So we're probably going to be expanding to other sources of UTC out of Europe in the future.
I think to Eric's question, it's more like what's the uplink to the satellite in terms of like your UTC? Do you go via the Iridium network, or you're directly like having a link to the STL module?
It's part of the Iridium network.
Oh, the Iridium network. Okay.
Right. Iridium maintains all uplink communication throughout the world for their constellation.
So you have something like PTP basically running over that.
It's not PTP. No, not at all. This is very much like GPS, where we're sending corrections to the ranging data.
Yes.
So out of the so many satellites, right? How long can it sustain about the Earth without being refilled or recharged? Like, how long can it run? Because you may have to do maintenance at some point, right?
Theoretically, the life is at least 20 years. Whether they last longer or not, I don't know. Probably 25. I think is probably pushing it for the technology. Iridium, as I said, they just relaunched the entire constellation in 2019, and they deorbited all of the entire older constellation. So they would probably do it again. We are only one part of the Iridium business. They do a significant amount of business with their cellular type, well, satellite sat phones and all kinds of services that they provide over the Iridium network. They have a lot of interest to keep that going.
Cool.
Yeah,
I see.
I have one more question. I'm trying to build this mental model of this a little bit. So sorry for the kind of basic questions, but The other thing I was wondering was that what's the delay spread characteristic of the signal? Because you have, you know, kind of multiple overlapping beams that has to happen as these satellites, they orbit, and so you're losing coverage on one and you're gaining coverage, and then there could be some environmental concerns, like you could be close to a large body of water or whatever. So what is the practical limitation for delay spread in the signal? Like how many satellites could I receive at the same time? Maybe is a different way to ask that.
Yeah, that's not a problem. We compensate for the Doppler, of course, and a number of other space varying parameters. But I would probably say the Doppler would be the most aggressive calculation that needs to be compensated for, which you could see the math. It's about 30 kilohertz plus or minus as based on the velocity. And it becomes advantageous at that point to receive more signals. Each one will have its own, think of a multi-finger rake receiver like in GPS, right? So you'll have multi-finger rakes to analyze the different satellites, and then you can combine the numbers into the Kalman filter from that.
And these are orthogonal signals, or are they or just
yeah it's a digitally modulated QPSK that can be converged orthogonally.
All right, thanks, that helps.
Hey, Charlie, I had another question. I apologize if you answered it already and I may have missed it. But the control stations, back to, I use the GPS model, right, to describe. How many of those does Satelles have?
Well, that's proprietary, but we have enough to maintain a worldwide accurate constellation.
Okay.
I have one more question. It's okay if it's proprietary, but I saw it's okay. I understand that answer. I will email you later.
Okay, that's fine.
You shared kind of scale and dimensions of the receiver, what it would look like on the ground to install it in a deployed location. You shared the big picture of the satellite with some broad dimensions. Can you give me a sense of like your specific module? Not how big are the satellites, but how much, like what's the size, weight, and power used by, like, is your STL stuff a specific component, or is this a software algorithm running on the Iridium hardware? And if it's a component, like how big is it, and how much power does it need? And
so
if it's software, I'm talking about the transmitters.
Oh, the transmitters. Oh, so that's part of the I'm sorry, let me
like, did you design and build your transmitter part of it? Like, I know it goes through the Iridium radio, you said, but like
we do not have our own transmitter hardware. We're actually utilizing, sorry, I'll find that picture there. We're part of the Iridium satellite. We're actually using one of their transponders there.
Nice.
Right. Do you have custom hardware on board in addition to the transponder?
We are part, yeah, we're using their transponder.
Right.
We don't have our own specific hardware embedded in the satellite, no.
So it's just like a software application running hosted on their platform.
Yes, that's correct.
Okay.
That's
okay,
amazing.
thank you.
But that's great, but also makes it like dependent on the architecture of the Iridium, right? Like there's certain things.
That's true. Well, okay, so we can adopt to another satellite constellation if we needed to in the future.
Yes.
This is just what we're doing now. We're using one of the Iridium transponder channels exclusively for PNT. Can we use some other satellite constellations transponder? Yeah, sure we can. Again, it's got to be, with the same frequency band. If it can shift itself over to accommodate, where we need it to transmit, yes, we can accommodate that as well.
This is where I'm going with it. Like that's where my thoughts are going. So.
Yeah.
Okay. Yeah. Absolutely. It's a scalable system. Yes. And just, I know you could email me offline, that's fine. I'd love to hear from you, but keep in mind too, this is so much more modernized over GPS, right? The cross links make a big difference in how many actual, now you still need a lot of ground stations, but you can transmit up, and you know, you got a satellite passing over the North Pole, it gets this correction. So when it comes back down over the continents, it's already got it's ready to go. It's tweaked. All right. So you don't have to have ground stations like in GPS. There is no cross link. So the only time you can talk to it is, oh my gosh, I can't wait till it goes over one of my ground stations so I can see what it's doing and send a correction to it. You don't have to do that with the Iridium. Crosslinks solve all that. It just pushes it up into the modern technology. I don't think anybody looking to launch satellites today, a constellation, is not going to do crosslinks. It's just too much sense.
A tricky question that I will not be surprised if you cannot answer it is, I mean, it's also like an elephant in the room to me, is this can be perhaps also implemented on Starlink, right?
We can adapt to any technology that accommodates our frequency.
Yes.
Right? Most satellites up there, regardless of their name, they're all software-defined radios. But the problem is, what kind of limitations did they put around their SDR design? If they can accommodate our L-band frequency, we can adopt it very quickly. If we want to go to, say, an X-band in the future, that's another discussion. But as long as the SDR can accommodate the L-band, it's absolutely a consideration that can be considered.
Amazing.
Oh, I don't think that was the elephant. The elephant is this is a subscription service, right? So I can't build a receiver to actually receive this without paying for it, correct?
Good question. I'm wondering when someone's going to get to that one. I love elephants. Bring them on. But yeah, that is absolutely true. Yes, we have a very modest subscription for this service. From what I've researched, we are significantly lower than some of the GNSS augmentation services that I've been seeing out there. They charge an incredible amount of money, some of them. But it can be considered to be integrated either with all in full when a receiver is purchased by someone to use. They could prepay like a 10-year subscription up front, or just get it for a year and see how they like it, renew it for another year if they want. There's different ways. We accommodate a variety of situations for that.
That's great.
Cool.
All right. Any more questions?
Sorry, I have a dumb question. Not knowing much, I haven't heard much about the geo being stationary about the Earth. How does it maintain geo's stationary? Does it move or rotate
Geo's,
according to?
yeah, that's the there was a, I can't go backward easy. Let's see here. That was this picture. Yeah, the geostationary satellites
Yes.
are in an orbit that they rotate at the exact same rate as the Earth, and so they appear not to move.
Okay.
Now they do get they got little thrusters on there where there's a grid that on the ground they're trying to keep them in the grid, but they don't move. And so that would be like the satellite TV services. There are also some PNT over China, Japan, the United States use this. They call them SBAS, space-based augmentation satellites. That they're geosynchronous. They're just fixed over a particular part of the Earth. So yeah, you could do a lot of research on that. It'll explain it better than I probably just did right now. But hopefully that helped.
Eric also looked into so this is geostationary and there is also geosynchronous, and like I think if you look at both of them at the same time, you will enjoy it.
Okay. Is GEO also a group of satellite or just one?
It's a distance. It's like 35,000 kilometers. That's like considered geo. That's because of the 9.8 from Earth and the 24 hours for 360 degrees, more or less. Leap second, people don't get mad, of the orbit of the Earth. But like you
No,
sit
no.
in orbit, yes.
My question is that made up of a group of satellite or just one satellite?
No, no, no. Of course, it's made up. It's imagine like you look at Saturn and like the rings is basically a ring. That's
Okay, got it.
the ring is geo stationary, and
Uh-huh.
then if you go in that sphere, you sit in the sphere, not in the ring, then you will be geosynchronous. It means from Earth,
Okay.
you're not just in a spot, you're going through a like a 8 shape, you know.
So it's the first diagram on the left, right? That's what the geo
These are
is, right?
middle. These are middle
Yeah,
Earth
it's
orbits.
a
This is the
neo.
GPS
Yeah.
constellation. So if it was GEO, I don't know if you can see my mouse. It'd probably be off the chart a little bit. Be way out here somewhere.
Oh,
All right, that would be GEO. So this is
okay.
middle Earth orbit, and then this
Uh-huh.
is low Earth orbit. And Iridium is a low Earth orbit. So are OnStar. There's a number of low Earth orbit constellations up there.
Got it. So the GPS resides on the MEO?
Yes.
Correct. These
Okay.
are considered
Okay.
middle Earth orbit constellations.
Got it. Thank you. Yep.
You're welcome.
All right. We top of the hour. We started on time and we're gonna finish on time, I guess, unless there's any more questions. And also, Charlie, is there any like a link or something if someone is interested to reach out for subscription or something? Did you provide that, or you just go Satelles?
You can email me here or go to our website is satelles.com,
Perfect.
www.satelles.com, and we have a lot of information there. You could either contact me directly or take a look at our website, and that might answer some questions you have as well.
Wonderful. Wonderful. All right. Then we'll adjourn and see you guys next week. All right.
Okay.
Bye, everyone.
Thank you, everyone. Bye.
Thank you. Thank you. Bye-bye.